All right, today, that's what I want. Today we are looking at another coordinate system. It's called the polar coordinate system, and it's an alternative to the Cartesian coordinate system we're used to using. But the two are closely related, and I'll show you how they're related in a minute. But before we get to that, so you can have polar graph paper, and here's an example of some polar graph paper. So this one here. So here we've got the pole at the middle, and so everything's measured from the pole, and so each of these circles might be 1 unit, for example, and then we've got some angles, so it's pi on 6, so each of these is divided into pi on 12, so that's what a radian measure one would look like. Here's a degree one, so again you've got circles representing the units from the pole, and then degrees around, and so that fits in here like this. So polar coordinate system uses the distance r and the direction theta from the pole, and could be, you saw those on those polar graph paper. Here's the pole, so the distance from, so 1, 2, 3, this where I've got my hand here, it's 3 from it, and 15 degrees. All right, so we know what that point is. Okay, and so it's written r theta, so the distance and then that angle. And theta is measured anti-clockwise from the positive x-axis. So there's our polar graph paper, positive x-axis, so the same way. All right. So of course you could overlay Cartesian coordinate system on this. So here's our, if I did have it on a Cartesian coordinate system rather than that polar graph paper I showed you, would be like this. Here's our x and y axes, and our pole is the origin, and so we're a distance from the origin and an angle up here, so r theta. All right, so point P here, this one here, has polar coordinates r theta, then its Cartesian coordinates would be given by. All right, so in the x direction, so if we're looking at here, we've got a triangle that I've got already. So this side here is adjacent to the theta, so this side here, its length would be r cos theta, and this side over here is away from or opposite to theta, so that one would be r sine theta. So of course this adjacent side running here along the x-axis here, that's the x value, and so the x value in Cartesian is r cos theta, and the y value in Cartesian, because y is this way, that would be r sine theta. So there's the relationship between polar and Cartesian. And if we think back to our parameters, then our angle here, theta, is our parameter. Oh, excuse me. Excuse me. All right. So if point P, for example, had, let me get rid of that stuff. All right, let's get rid of all of those things. And so if instead of r theta, we had P was x, y, and so this length, the adjacent is our x value, our opposite is our y value. Then looking at this triangle that I had drawn before, we can work out our r and our theta in terms of our x and our y values. And so we can do that quite simply, because if we do our old friend Pythagoras here on that, because that's a right angled triangle, x squared plus y squared equals r squared. Alright, so r squared equals x squared plus y squared. Or if we take square root of both sides, r is the square root of x squared plus y squared. And then, of course, if we've got the coordinates x and y, so we've got the opposite and the adjacent, and opposite over adjacent is tan. So tan theta would be x over y. So if you like, theta is tan minus 1 of x over y, or is the wrong way, opposite over adjacent, not adjacent over opposite. Silly me. Opposite, which is y over x, y over x. And of course there's a restriction there that x cannot be equal to 0, otherwise it's undefined. All right, the tan value, that is. All right, so there's our polar coordinate system. There it is overlaid on our Cartesian. Here's how we get our Cartesian values x and y from the polar stuff, that values we've got, the r and the theta. And here's how we could go the other way. So let's have a look at some examples. So it says here, convert the polar coordinates 2 and 5 pi on 6 into Cartesian coordinates. All right, so 5 pi on 6 would be around over here, and that's a radius 2. And so we're looking at what we're after. So x is equal to cos theta, and our r is 2, so it's 2 cos 5 pi on 6. Now cos in the second quadrant here is negative, so it's 2 times negative. And 5 pi on 6, our reference angle here is pi on 6. And the cos of pi on 6 is root 3 on 2. 2's cancel. So our x value is negative root 3. Our y value is sine theta. And that's 2 sine 5 pi on 6. And sine is positive in the second quadrant. And the reference angle pi on 6, so that's 1/2 the sine of pi on 6. So 2 times 1/2, of course, is 1. So our Cartesian coordinates of point P are negative root 3 and 1. All right. Now, there is what we might term a non-uniqueness of polar coordinates. So a point on the plane could be represented in a number of different ways. And so here's an example I'm going to do here of 1 and pi on 4. So if I go here with my Cartesian plane, here's my x and here's my y. Pi on 4, so I'm just going to put a line here like so, and that angle in there is pi on 4. And we're told that the radius is 1, so let me put my point out here, and that point there is 1 and pi on 4. All right, now that's one way we could actually describe that, but we could describe that in other ways. This is where non-uniqueness, if you like. So if I went from here all the way around to there, which because that's pi on 4, so is that, which would be 5 pi on 4. A radius of 1 would put me out here. Now, we don't want to be out here, we want to be over here. So rather than a radius of 1, if I can say, all right, we'll go a radius of -1, for example, instead of heading out that way, we'll head back, -1, that would have me at the same spot. All right, and another one, I'll go another one, let's go purple. So instead I could go all the way around to there for my angle, and that angle all the way around to there, well, it's 2 pi plus pi on 4, which is 9 pi on 4. So I could also, and then a radius of 1 out, of course, and so I could also write that as 1 and 9 pi on 4. All right, so when we say the non-uniqueness, all it means is that it's possible to describe a location, a point on the polar coordinate system in a number of different ways. All right, more often than not, we just use this first one, but there are others as well that we could do. So, for example, a couple of examples, and then that would be it for today. Let's go back to the blue. So for each of the Cartesian coordinates, find 2 representations using polar coordinates. So these are Cartesian coordinates. All right, so I'm going to actually change my thing back for the moment. Let's go, I'm going to put a red line right down the middle, and so I'm going to work on the left and on the right. So on the left here, I've got, let's put 1 and √3. So here's our point, which has coordinates 1 and √3. And so our r, of course, is just our distance from there to there. That's our r. Now, if I go down here and triangle, then this is 1, this is √3. So to find our r, of course, is the square root of 1 squared plus √3 squared, which of course is the square root of 1 plus 3, which is the square root of 4, which is 2. And then what we want to do is we want to know what this angle, so it asks for 2 representations, so I'm just going to look at one here where that's theta, and theta will be tan minus 1 of the opposite √3 over 1, and if you refer back to your triangles or however else it is that you remember your sine, cos, tan values, you'll find that that's pi on 3. All right, so one representation of this in polar form is the radius 2 and the angle pi on 3. Now, of course, from what I mentioned before, I could, if I continued that like so, we could go all the way around to there. Now, that angle all the way around to there is pi plus pi on 3, is pi on 3. But of course, the positive radius would put us out here, so we need to go negative. So another way that we could do it is -2 and 4 pi on 3. All right. And so the relationship between these two things, of course, for the angle, we've just added pi to the angle, and for the radius goes from being a positive to a negative one. All right, so two different representations of this point in polar, Cartesian point in polar form. All right, the next one that we're going to look at is 0 and -2. All right, so for our, just notice I've got it incorrect in my notes, isn't that handy? All right, anyway, not to worry, I'll do it correctly now, and then I'll go back and change my notes. So 0 for the x value, -2, that brings us down here. So it's this point here. So we want two representations. All right. So one of those representations would be, do it in orange, is if we go from here and we go all the way around to there. Now that angle is 3 pi on 2. And the radius, so we don't need to worry about the negative because the radius is just the distance from the pole, and that distance from that pole is 2. And so for that point, we could say that it is 2 and 3 pi on 2. Now, another representation of that could be the following. So instead of going all the way around there, what about if I just go to here, and instead of a radius of 2, I go a radius of -2. And so that's pi on 2 there for that angle. So another representation could be -2 radius, pi on 2 angle, and that takes us to the same point. All right, so that's it about polar coordinates and 4 polar coordinates. So you've got some exercises to do to help to play around with those things that we've looked at there before we do some more stuff, i.e. graphing with the polar coordinates. So if anything's not sure you're sure of there, make sure you get some assistance, and as always, have fun.